Hello everyone, my name is Mingyue Zhang, and I am a PhD student from Peking University. This paper is a result of cooperation between Waseda University and Peking University. The authors are Jianong Li, Professor Haiyan Zhao, Professor Ken Jite, Professor Shiji Honida, and Professor Zijin. Professor Zijin is my supervisor. The MapK loop is a typical framework for self-adaptation. There are 5 activities in this framework: M. Monitor, A. Analyze, P. Planning, E. Execution, and K. Knowledge base. If we take the self-adaptive system as a black book, the interaction between the system and the environment is similar to the reinforcement learning. Thereupon, we can leverage the learning technique to enhance its adaptability. A self-learning adaptive system, SLAS, a kind of self-adaptive system, uses machine learning to enable and enhance adaptability, and SLAS is expected to learn from its interaction with the environment to generate and evolve its adaptation policy with the environment dynamics. However, there are some limitations of SLAS, resulting in performance degradation at runtime. When current environment or systems are changed, the model is revised, and based on the revised model, an adaptation policy is replanned for runtime usage. The replanned approaches, especially ones based on machine learning, are time and resource consuming. This table shows the replanning or retraining time when the settings of the environment are changed. For example, at the beginning, we use reinforcement learning to plan a movement policy for Mojuka ant. The ant is a robot with 4 legs. After training process converged, one leg of the ant is broken. Then we still need about 4 to 10 hours to train a new movement policy. For many real-world applications, it requires that SLAS should quickly respond to the dynamic of the environment or system and involve a new adaptation policy in a very short time. The traditional SLAS cannot cope well with the applications. First, to illustrate our main idea, we show a running example about 2D navigation. A mobile robot is ordered to drive from a start location to a goal location in a building. The mobile robot is equipped with a laser finger and uses SLAM to sense spatial environment. Due to the limitations of SLAM, the spatial environment is partially observed to the robot. The accuracy of the robot's sensors and motors may be low or high. Because of different users' objectives, there are various start location and goal location. The traditional SLAS needs to know all configurations of the environment and the system, and the nerd policy is bound to the configurations. That is, we fix the configurations, for example, configuration 1, and train a policy. If the real application is configuration 3, we need to spend a lot of time retraining. We propose a meta-reinforcement learning adaptive planning (MRAP) approach for quickly evolving the adaptation policy at runtime. This approach enables the SLAS to quickly adjust its policies online at the cost of offline training. There are 3 phases. Offline training, that is, for training a meta policy. First, submodels on the spatial environment, the system capabilities, and the objectives under different assumptions are defined. Second, these submodels are synthesized into integrated dynamic models represented by MDPs, which constitute a model base. Third, a meta-reinforcement learning algorithm learns a meta policy over these MDPs in a model base. Online adaptation, that is for generating a real-taking adaptation policy, that is meta policy. The adaptation algorithm takes meta policy as its initial policy and interacts with the actual environment. Based on the response of actual environment, the algorithm updates the current policy to produce an adaptation policy suitable to the current environment. Online execution. In this phase, the targeted system takes action based on the adaptation policy generated in the online adaptation phase, so as to complete the task of meeting the objective in actual environment. By following the principle of separation of concerns, we distinguish three aspects that are related to adaptation policy. That is the spatial environment, the system capability, and the user's objectives. In this paper, we introduce meta-learning into self-adaptation. Meta-learning is one of the most active fields in machine learning. It aims to train models that quickly adapt to new tasks by using only a small amount of training data and converge in a few training steps. After designing a set of MDPs, we take them as training data and use meta-reinforcement learning to train a meta policy. This slide shows the mathematical formulation of using meta-reinforcement learning to achieve quickly online adaptation. Finally, we propose a new self-adaptive framework shown in this picture, incorporating meta-reinforcement learning based on the MIRAP approach and the MapK loop. The knowledge base saves and manages a set of MDPs designed in the offline phase. The meta policy generated by learner and the adaptation policy adjusts to real scenarios in online phase. The purpose of these experiments is to answer the questions. First, adaptability. Compared with the baseline approach, how fast does the MIRAP adapt to real environment system dynamics or users' objectives, and what is the quality of the policy after adaptation? To better show the adaptation process, the x-axis are logarithm scales from the converge perspective in this picture, and A, B, C, D. The offline cases cover the real environment system dynamics, and E, F, G, H. The offline cases do not cover the dynamics cases. From the course perspective, AE shows that the objectives are changed, and BF shows that the environment are changed, and CG shows the targeted system changed, and DH shows that all three concerns are changed. We tried to find a perfect trade-off among the training time, converged episodes, and mean rewards. The values after normalizations are denoted T. The utility of the slash is showing this function. And the online performance. This slide shows that MIRAP performs better than the baseline. The baseline is OPE, online policy evaluation. And there are some limitations of our work. At development, there are two aspects to be further considered or enhanced: the same task, the definition of the same task, and how to model user's objective. And at runtime, there are three aspects to be further considered or enhanced: safety. That's all. Thank you.